All right, hi everybody. Let's get after our second lecture for this 1.2 unit. We're going to look at horizontal projectile motion. Okay. So for kind of the whole goal of kinematic motion, like the end thing, is to be able to explain and a good analytical idea of when objects fly through the air, what are the various things occurring to them? It's kind of culmination to this kinematic stuff. Now, no, I'm not expecting you to go out into the real world with a calculator and a pencil and pen and be like, well, if I throw the ball at this exact velocity and this exact angle, I know exactly how far it's going to go. No, come on. But if you kind of think about it, you do that already. Think about you yourself, you're lazy, you crumple up a piece of paper and you throw it towards the trash bin. Well, through practice, you kind of know how hard you need to throw. If there's an obstacle in the way, you kind of need to throw at a little angle, all that kind of stuff. So you kind of actually already do a lot of this stuff we're going to cover. We're just kind of giving a more analytical approach now for it. Okay, we're going to start with stuff horizontally. So horizontal, moving in the x-axis. Okay, so let's start by setting up x-axis, y-axis. Okay. We're going to base this all off of this one situation of we have some cliff, 9 meters tall. We have some object, and this object is launched off the cliff. Okay? Now, because this object is launched off the cliff, it's going to kind of begin to go, and then it'll eventually begin to fall to where it hits the ground. So let's take a look at what's going on the x-axis, what's going on the y-axis that we can kind of figure out. Well, first and foremost, y-axis. Well, this object is flying through the air. Anytime an object flies in the air, in the y-axis, there's always gravity, and it's always that negative 9.8 meters per second squared. It's kind of an always. The second thing is, this object is launched initially horizontally. So it's initially going in the x-axis the moment it's launched. That means the velocity initial in the y is 0. The moment it's released, it has just solely a horizontal component to it, nothing vertical. Now, we can take a look at its motion via the vertical stuff. We can kind of say this. The moment after it's released, yes, it's going to have some sort of acceleration due to gravity. And it'll have a little bit of velocity in the y. Just a smidgen. Small vector. Remember, vector has both magnitude and direction. Magnitude, number. So, as this object is going, these things occur. But, because the acceleration vector and this velocity vector both point vertically downward, it's going to speed up in the y-axis. Meaning, at various points, the velocity vector should get longer and longer and longer. Whereas the acceleration vector should stay roughly the same because gravity is a constant, meaning it never changes whatsoever. Okay? Now in this class, I've mentioned before that there is no such thing as air resistance. Yes, air resistance is real. You go outside, stick your hand out the window. While you're moving your vehicle, you'll feel some wind push against your shoulder, against your arm. That's air resistance. While there's air resistance in real life, for this class, we're going to say, hey, air resistance, not a real thing. So what that just means is, in the x-axis, there's just one thing, and that is your velocity x of the ball. So, because in the x-axis there's just this one and only vector, I could state that the v initial x is equal to the v final x, that those are both the same. Well, because these two are the same, and the direction staying the same the entire way, so magnitude, number, is the same, and then direction, all pointing towards the right, the acceleration in the x-axis is 0. Now, these 4 things are in always. Meaning, if you're ever given a question where an object is launched horizontally, automatically, boom, 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 boom. These 4 things you can list out. Really 3, acceleration, velocity in the y, and acceleration in the x. These three things you can list out. Maybe sometimes you're given a velocity in the x, maybe not. But, you at least know it's going to be the same throughout. Okay? Now, let's take a look at equations. Now, we're using just our three kinematic equations, okay? And if we think about it, in our x-axis, the only one that's actually viable because the other two equal themselves out. In the x-axis, we end up just with this. Delta x equals v initial x t. Now, we know delta x is your displacement, t is time, v initial x is initial launch velocity. How it might be worded more often than not in this next unit would be like, delta x is how far did it go? T, your flight time, how long it was in the air. And v initial x, just for horizontally launched objects, would be your launch velocity. Those would be commonly how it's stated. For the y-axis, oops, is it x again? Y-axis, sadly, all three of them are viable at one point or another. Yes, you could cancel out the v initial in the y because it's always going to be 0. But I'm not going to do that for this one because I don't want to confuse you guys and gals later on. Okay? So here's our equation. So in this one, sorry, I wrote t squared x, and it's just t. So let's solve this question out. Let's say, how far are we going if we know the launch velocity was 12 meters per second? Okay? So I'll use purple actually. Got all the pens in the world. Okay. So we're trying to find how far it goes. So we just have the one x-axis equation, delta x equals 12. That's our launch velocity times some time. We need to find time. This is where the y-axis comes into play. The reason why I can say the y-axis comes into play is because this object is dropping 90 meters. Okay? So that means that, tell me is, the time it takes it to drop 90 meters should also be the same amount of time it takes it to go from where it begins to wherever it lands. Those should also be the same. So I can use this equation. The one I put a star next to, this is kind of your bread and butter for horizontally launched objects. I'm not going to say it's always one you're going to use, but it's a good guess most of the time. So delta y equals v initial y t plus 1/2 at squared. That's 0 always. So negative 90 equals 1/2 negative 9.8 t squared. Now, remember, this 90, because the object is dropping, the delta y is negative 90. Anytime you go from a high to a low, your delta y is negative 90. So this would be a 9 right there. Okay? That's why that's negative. So, anywho, you get that. Divide both sides by 4.9, negative 4.9 of course, and you get a t squared is equal to 18.37. Square both sides. T is 4.29 seconds. If you rounded, your number might be slightly different. Exact numbers right there till then. Anyway, so take that number, plug it in, 4.29, and you should get a, let me make sure this is right. .43 meters. How far it goes. Okay. That's all I have for this. Until the next time, kiddos.